On the source of T1 weighted contrast on MR images. I mean, this seems like a pretty simple topic, but I think it gets overlooked as we talk more about advanced MR techniques like susceptibility weighted imaging and ASL and the like. So as we think about MR, the way we recognize that these are T1 weighted imaging is that the fat appears to be of high signal intensity and the ventricle is dark. So if we're collecting information in this fashion from a spinning net magnetization vector from the protons with our antenna, and then we see this sine wave from the passing magnetic field inducing a current in the antenna. How is it that we can tell what tissues are of short T1 relaxation time and what tissues are of long T1 relaxation time? So in this discussion, I think it's important just to recognize the drawings that I'm giving you, and you may be familiar with them from your own reading and experience, but these drawings are done in a sort of a classical model of physics, in the sense that we're not looking at a single proton, we're looking at the net magnetization of all of the protons that are aligned with the magnetic field. And we know those protons are not stationary, but are precessing around this axis, which represents the long bore of the magnet, or in a sense, the direction of the large magnetic field. Now, as we put energy into the system, this net magnetization vector starts to veer off its baseline position. And so the advantage of this drawing of this rotating frame of frame is the notion is that the frame is rotating at the same rotational velocity as this proton vector. And of course, that rotational velocity is based on the Larmor equation and of course, the strength of the magnetic field. So for our drawings, I don't need to draw a moving vector. I can have it stationary because the framework is moving with it. And in the same way that if you're talking to someone on a merry-go-round, even though you're moving around, that you seem as stationary to each other. And so eventually we end up with this vector by putting in radio frequency energy at the appropriate frequency. We can move the net magnetization vector into the transverse frame. And of course, this is where the protons need to be if we're going to collect signal. So again, if the protons are aligned in this direction, we get, in a sense, no signal. Even though they are aligned, we need to displace them from their stationary frame to get signal with our antenna. So what are these drawings showing you? These are, in a sense, a representation on this rotating frame of T1 and T2 relaxation time. Remember that T1 relaxation time tells us what's the time it takes for return to baseline. So as this vector gets shorter, this one will get longer as they recover out of the transverse frame back into their baseline state. And so that number, that time, is described as the T1 relaxation time. Or in fact, the T1 time is about 2/3 of recovery from this excited state. T2 relaxation time all occurs in the transverse frame. That's the time of dephasing of the protons, because when they come down initially after the 90-degree pulse, of course, they're homogeneous in phase, but then there's phase dispersion that goes on over time. We're not going to talk about that today. We're just talking about T1 relaxation time and T1 contrast. And just as a reminder, this drawing, this is our pulse diagram, and we give, for a simple spin echo sequence, this is not fast spin echo, this is, sort of where MR started. We have a 90-degree pulse, which is that RF pulse that excites it into the 90-degree plane. There's a 180-degree pulse, which is the rephasing pulse, which gives us our echo at 2 times this distance. And then there is a second 90-degree pulse. And then, of course, there'll be a whole series of 90-degree pulses. So if we want to create a T1 weighted scan, you may have learned that you look at the timing parameters on the text, and you're looking for T R times that are in the order of 200 to maybe 700 milliseconds. That means that this interval between pulses is relatively short. What happens then is if we compare the behavior of fat to the behavior of CSF, because fat has a short T1 recovery times or relaxation time, that's one of its basic behaviors. This is not something that we've given it. It's the nature of that tissue that fat recovers quickly. Once we excite it in the transverse plane, it recovers quickly back into its baseline state. Where CSF, actually all fluids, water, they have a very long T1 relaxation time, just as they have a long T2 relaxation time. And that's the nature of fluid. And so because it takes a long time for those protons to recover, if we look at what's happening in fat compared to CSF, a short time after the excitation pulse, we see we have more recovery in the fat. Now, how does that give us contrast? The more protons that we have that have recovered, the more protons we have in the transverse plane, because I can only excite the protons that have recovered back to baseline. So if you think about this as a vector of 10, let's assume that the proton density in CSF and fat are about the same. We start out with a 10 vector. If we look maybe 200 milliseconds later, we may have only recovered 1/10 of the protons, whereas in the fat, we may have recovered half or more of the protons. So that means when we give the next 90-degree pulse, we have a longer longer vector, and that means there's more protons in the transverse plane to give us signal in our antenna. So more protons, we get more signal. And so that's why on a T1 weighted scan, we see there's higher signal intensity in the fat and less signal in the brain, and even less signal in the CSF. So to just reiterate, it is the timing of the excitation pulses, the RF pulses. By bringing them close together, we have enough time to get some recovery in the fat because of its short T1 relaxation time, but not enough time to see very much recovery in the fluid. And so we have very little, a small amount of protons to excite, and we get low signal in the fluid. So there you have it, T1 contrast. Now we'll use similar drawings to talk about T2 contrast, but again, those concepts will serve you well as you try to understand the relationship of the pulse sequences to the tissue characteristics.